Welcome to the class 4 of the chapter 4 moving charges and magnetism, which is being taught as the unit 3 in physics class 12. So till now we had learned about Biot-Savart's law, okay, where we understand the relation between the magnetic field and the current, okay, and then we also learned Ampere's law, okay, so which has a similar relation to the Biot-Savart's law as Gauss's law had with Coulomb's law, as we had seen in electrostatics. So till last time we had understood the Ampere's circuital law, or Ampere's law, which could be understood for either infinite wire or a circular loop. Okay, so for a circular loop we had, so for Ampere's loop, for a circular loop we had found V is equals to mu 0 I to pi r. Okay, so this is the Ampere's law that we had found. Okay, so based on this Ampere's law, okay, we will try to see how and other kinds of systems can be explained, other kinds of magnetic systems, okay, so where we will be calculating the magnetic field. Okay. So two such devices that we will be looking at is solenoid and toroid. Okay, so these are equipments and they can generate magnetic fields. Up until now we had seen how a current carrying wire or loop, okay, what kind of magnetic field is associated with that current carrying loop. Okay, now we are going to learn about two devices that can generate magnetic fields. Okay, the synchrotron uses a combination of both. Okay, a synchrotron is another device, okay, which uses both a solenoid and toroid to generate high magnetic fields. So we can then suggest that in solenoid and toroid we will find high symmetry, okay, where we had already discussed this in the last class, that Ampere's law requires symmetry for it to be applicable. So solenoid and toroid are two such devices where Ampere's law is valid and we can apply it. So what is a solenoid? So you can see over here, okay, so this is kind of the diagram, and you can see the different kinds of magnetic field that is generated. Okay, so this is a section of a solenoid, and they have, it is a stretched illustration of a solenoid, of a section of a solenoid. So you can see that only the exterior semicircular part is shown. Okay, and the second one, you can see that if suppose we consider a finite solenoid, we will see how these two differ. Okay, so this is the magnetic field that is associated with a finite solenoid. Okay, so if we are considering a long solenoid, what does that mean? Solenoid's length is larger compared to its radius. Okay, so the length of the solenoid will be larger than the radius if we are considering a long solenoid. And what does it consist of? It consists of a long wire which is wound in a helix form. Okay, we had learned about what is a helix. Okay, so it's in a helical form, and the neighboring turns are closely spaced. Okay, so these turns that we see, okay, these turns that we see over here, they are actually very closely spaced. Okay, the turns are very closely spaced. Then each turn can be regarded as a circular loop. Okay, so when we are considering these as a circular loop, that is where then we can use the Ampere's law, okay, to get the magnetic field. So over here, as I had already discussed, the figure that is present over here, okay, it displays the magnetic lines for a finite solenoid. So there is a section of this solenoid in an enlarged manner. This is the A part of the figure, whereas the B B figure shows the entire finite solenoid with its magnetic field. Okay, so this is just a section of it. And over here you can see that the circular loops, okay, that the field between the two neighboring turns vanish. Okay, you can see that these are the circular loops that we are considering. Okay, and the field in between two consecutive loops will vanish. And in the B figure, it is shown that the field at the interior midpoint P is uniform and strong and along the axis of the solenoid. Okay, over here you can see that the magnetic field lines are directing along the axis of the solenoid. And if we consider exterior midpoint Q, okay, outside the solenoid per se, then we can see that the magnetic field over here becomes weaker. Okay, and it is along the axis of solenoid with no perpendicular or normal component. So this does not have any perpendicular or normal component, the field over here. So if we keep making the solenoid longer, okay, it will appear like a long cylindrical metal sheet. Okay, so this figure represents the idealized picture. Okay, you can see over here the field outside the solenoid is approaching 0, and we will assume that the field outside is 0. Okay, so since it is approaching 0, we are going to consider that the field outside the solenoid is 0. Okay, so we will be equal to 0 outside the solenoid. The field inside will become parallel to the axis of the solenoid. So if now we consider a rectangular Amperian loop, okay, so we are considering a rectangular Amperian loop A, B, C, D, A, B, C and D. Okay, so along CD the field is 0 as we have suggested over here. Okay, along the sections B, C and AD, the field components are 0. Okay, as you can see that the field component would be 0. Then these two sections will have no contribution towards the field that is existing, okay, over here. So the field that will appear along BC and AD has no contribution to the magnetic field that is present inside the solenoid. Then the field along AB, we can take that as B. Okay, so field along AB is B. So the relevant length that we are going to consider for this Amperian loop is L is equals to H. Okay, H is the distance between the AB. Okay, and this is a loop, so the length of the loop will be AB. Now since we have already said the solenoid has a lot of turns, okay, so N will be the number of turns per unit length, and the total number of turns will be N into H. Okay, so H is the length and N is the number of turns per unit length. So the product of it will be the total number of turns that is enclosed, okay, over here. What is the current that is going to be represented over here? That is going to be your IE. Okay, so that is your effect enclosed current, okay, and it will be depending on the number of turns that you have over here, the total number of turns. So that is going to be I into NH, where I is the current in the solenoid. Okay, so I is the current that is flowing through the entire solenoid, but since we are considering only this Amperian loop, we are going to consider only IE, okay, that is enclosed by this loop. So from Ampere's law that we have seen before, BL is equals to mu 0 IE. Okay, so we have already said that L is equals to H and IE is equals to I into NH. Okay, so over here you get BH is equals to mu 0 I NH. Okay, so when you cancel out HH, you can see that the magnetic field, okay, so the magnetic field with respect to the loop that we are considering depends on your permeability of the free space, the number of turns that are there, and also the current that is flowing through the solenoid, and the direction of the field can be given by the right hand rule. Okay, so suppose over here, as you can see that this is the direction of the field. Okay, the solenoid is thus commonly used to obtain a uniform magnetic field. Okay, so solenoid gives you a uniform magnetic field. Now we come to toroid. What is toroid? Toroid is, suppose you take a solenoid, okay, which has these turns, and you turn the entire cylinder into like a circle. Okay, so what is toroid? Essentially, it is a hollow circular cylinder, circular ring. Okay, it's a hollow circular ring, and there are large number of turns, and that are again very closely spaced together. So as I said, it can be viewed as a solenoid which has been bent into a circular shape to close on itself. Okay, so if you take a long solenoid and then you turn it into a circle, okay, so that is going to give you a toroid. Now in the A figure, okay, in the A figure we can see that current I is being carried by the toroid. We shall see now what would be the magnetic field on in the open space inside inside and exterior. Okay, so point P is inside the toroid and point Q is outside the toroid, and we will try to find out the magnetic field at both the points. So magnetic field inside the toroid is constant in magnitude for the ideal toroid of closely wound turns. Okay, now we are going to consider a sectional view of the toroid. Okay, what is a sectional view? Like if you cut across the toroid, you will try to see what is there inside. Okay, so this is a sectional view. So direction of the magnetic field inside is clockwise as per the right hand thumb rule of for circular loops. Okay, so clockwise as in it is going to be the field direction is going to be like this. Okay, this is the field direction. Okay, so it is actually turning like this. So if your fingers turn like this, okay, you can even find out the direction then. So you have three circular Amperian loops over here, 1, 2, 3. Okay, so 1 is the inside one, this is 2, and this is 3. Okay, so you have 3 Amperian loops over here and they are circular in nature. Then by symmetry, the magnetic field should be tangential to each of them and constant in magnitude for a given loop. So all the field, okay, on the circular loop 1 will have tangential direction and will be equal in magnitude, whereas in the circular loop 2, okay, so the magnetic field in circular loop 2 will be equal in magnitude at any point on the circular loop 2, and similarly for circular loop 3. Now we can say that the circular areas are bounded by loops 2 and 3 and they both cut the toroid. Okay, so 2 and 3, and this is the the toroid, the turns where they are intersecting the the plane. So each of the each turn in these will be carrying a current, okay, and it will be cut by the loops loop 2 once and by loop 3 twice. Okay, so this is what we understand from here. Now we will take loop 1, okay, and B1 we are going to consider that as the magnitude for the loop 1. So that using Ampere's law, okay, so we are going to consider the circumference of the loop. Okay, so let R1 be the radius of the loop 1. Okay, so L is going to be 2 pi R1, and the loop is enclosing no current. Okay, inside there is no current per se in the inside part of the toroid, okay, where the loop 1 is situated. So your I0 becomes 0. Okay, so your what will be your B1? So B, if you remember, we had taken as BL is equals to mu0 IE. Okay, so this is the Ampere's circuital law for us for a loop we are considering. So B L mu 0, and since we already said I is equal to 0, so this is 0. So B1 is 0. So this is what we have already seen, and we have already said that for a toroid, the magnetic field inside the toroid is going to be 0. Okay. So in the open space inside the toroid, the magnetic field is 0. Now we will try to see what will be the magnetic field at Q. Okay. Now we will say that magnetic field at Q is also 0. Okay, if you are going to consider. So now we will try to see the magnetic field that is existing in between or within the toroid. Oh, okay. So we are first going to consider loop 3 where we have B3. So again, because of Ampere's law, we are going to consider the length to be 2 pi R3. R3 is the radius of loop 3. However, from the sectional cut, we will see that the current coming out of the plane of the paper is cancelled exactly by the current going into it. Okay, so if you have the current going inside the paper at one turn, then the current is going to come out from the other turn outside the paper. Okay, so they will get cancelled out. So essentially IE, okay, for loop 3 is also going to be 0, and if that is true, then your B3 is equals to 0. Okay, so this is how we try to see that the magnetic field, okay, due to the third loop is also 0. Now we are going to consider the magnetic field inside the solenoid, and we will call it as B. Okay, so inside the solenoid it will be B. And now again we are going to consider R as a radius of the the toroid, and so we will have L is equals to 2 pi R as the total length. Okay, and the current that is there is going to be Ni. Okay, so it is going to be a product of the number of turns into the current. Okay, so that is going to be a IE or enclosed current. So then putting these in the equation, okay, so what we are getting is B is equals to mu 0 Ni by 2 pi R. So this is essentially what how you find the magnetic field that is existing in the toroid. Okay, in between the this entire region, this toroid region. Okay, so this is what we find. Now if we compare the results that we have obtained for toroid and solenoid, we will re-express it, okay, for understanding the comparison between the toroid and the solenoid. So if we consider R to be the average radius, okay, so R is the average radius of the toroid and N is a number of turns per unit length, then your total number, okay, is equals to 2 pi R N, and that is going to be the average perimeter of toroid multiplied by number of turns per unit length. Okay, so the big N is the total number of turns. Okay, and then what we get from here is B is equals to mu 0 and I. That is the result of solenoid. Okay, so if we put as we had got this, okay, we what did we get for the toroid? We got B is equals to mu 0 and I, okay, by 2 pi R. Okay, so if you substitute the value for N, okay, your 2 pi R gets cancelled. What you are remaining with is the number of turns per unit length, and this is the equation that we had got for the solenoid also. So in an ideal toroid, the coils are circular. In reality, the turns of the toroidal coil form a helix, and there is always a small magnetic field external to toroid. Okay, so we can say that the magnetic field that is present inside a solenoid is similar similar or equal to the magnitude of the magnetic field that is present even inside the toroid. Okay, so this relation helps you understand that. Now we will see what would be the force, the magnetic force that is existing between two parallel currents. Okay, so that is, we are considering two long straight parallel conductors over here. Okay, over here you can see there is a conductor A and there is a conductor B. Okay, and they are carrying steady currents IA and IB, and they are separated by a distance D. Now over here we can see that there is a magnetic field BA, or it is a magnetic field set up by conductor A at conductor B. Okay, so this BA is, it is generated by A at the conductor B. Okay, so this is what we are going to consider over here. And now these are placed near to each other, and hence they will have a magnetic force acting on each other. Okay, so as I said, that the conductor A is producing the magnetic field BA, okay, at all points along the conductor B. Now with the right hand rule, we can get the direction of this field, and that is going to be downwards. Okay, so if you consider the right hand rule, okay, so if your thumb points here and your right hand thumb and you're curling it, okay, so it is going to be going down. Okay, so that is where you see the BA is actually going downwards. Now with the help of the Ampere's law, okay, over here we are going to consider D as a distance between the the two conductors, okay, and just we are going to replace R with D, and this is the Ampere's law, representation of Ampere's law for the magnetic field that is present over here. Now conductor B is also carrying a current IB, okay, so there is a current flowing in IB, and it will experience a sideways force due to the field BA. Okay, so there is a force that is going to act on conductor B because it is placed in in a magnetic field. So we will call this force to be FBA. Okay, FBA, and this is going to be a force on the segment L of B due to A. Okay, so let's consider a segment of this conductor. We call it L. Okay, its length is also L. Okay, so we are going to try to understand what is the force that is acting on this L, okay, of B due to A. So the magnetic force can be given by IB LB. Okay, if you remember, we had seen that F is equals to I L B. Okay, we had seen this in the previous class, so using the same thing. Okay, so now we are putting in the values of B. Okay, over here. So mu 0 IA, this we get from the B over here. Okay, and then you have IB upon 2 pi D, and L. L is the length of the segment that we are considering. Now we can similarly compute the force on A due to B. Okay, so understanding the kind of the similarities between the conditions that we are for FAB and FBA, we can find that the two forces are going to be equal in magnitude but opposite in direction. Now this is consistent with Newton's third law. So for parallel conductors which are carrying steady currents, we can show that the Biot-Savart law and the Lorentz force both yield results that are correspond to the Newton's third law. So we can see from above that the currents flowing in the same direction attract each other. Okay, one can show that oppositely directed currents repel each other. Thus, parallel currents attract and anti-parallel currents repel. This is with respect to the magnetic field. Okay, so the force that is there due to the magnetic field, okay, generated by one conductor on the other conductor. Now you can see that this is actually, kind of the opposite sense of what we had learned in electrostatic, okay, where we had learned about the, like charges repel, unlike charges attract. So this is one of the differences that we find in electrostatics and, magnetic fields. And so now we will, represent the magnitude of the force BA. Okay, we had found the force BA. Now we will consider only the magnitude as the force BA per unit length. Okay, then we can then represent it as FBA is equals to mu 0 IA IB upon 2 pi d. Okay, so since we are considering it per unit length, so the length term goes away. And this is actually the expression that we use to define 1 ampere. Okay, so this is one of the 7 SI base units. We had already seen that, current is denoted, or the unit for current is ampere. Now we can describe it, or define it as that the ampere is the value of that steady current which, when maintained in each of the two very long straight parallel conductors of negligible cross section and placed 1 meter apart in vacuum, should produce on each of these conductors a force equal to 2 into 10 raised to minus 7 newtons per meter of length. Okay, so this expression helps you in defining 1 ampere unit. Okay, now this is, we understood how force can be calculated. Okay, so we have learned how force can be calculated. Okay, because because of the magnetic field that is generated by one conductor on the other conductor and vice versa. Now, as we had seen even in electrostatics, okay, so that if a force is present, there is going to be a torque acting on it, okay, which kind of, keeps it, it rotates the charge over there. So similarly, we are going to understand the torque on current loop and magnetic dipole. So we are going to consider torque on a rectangular current loop in a uniform magnetic field. Okay, so right now we are only considering uniform magnetic field. So we are going to consider a rectangular current loop. So we can say that the rectangular current loop that is shown over here is carrying a steady current I, and it is placed in a uniform magnetic field B. Okay, and this rectangular loop is experiencing a torque because of that. It does not experience a net force, but so this behavior, as I said, is similar to how we had, an electric dipole. Okay, so this was the dipole. The distance between it was 2a. Okay, and each of the pole had a dipole moment. Okay, so plus and minus. Okay, so we used to find the dipole moment. This was the electric dipole, and there was always a torque acting on the charges. Okay, so now we are going to consider similarly for this rectangular loop in a uniform magnetic field. Now we are considering the very simplest case where the rectangular loop is placed such that the uniform magnetic field is in the plane of the loop. Over here you can see that the two magnets are kept over here. So the magnetic field over here, you can see this is a magnetic field. Okay, this is in plane of the rectangular loop itself. Also, it is perpendicular to the arm AB of the loop and exerts a force F1 on it, which is directed into the plane of the loop. Okay, so the magnetic field will exert no force on AD and BC. Okay, so this is your AD and this is your BC. Okay, since this is, along this direction, there is not going to be any contribution to the arms AD and BC. And we can see that the the arm AB is actually is the arm where the force F1 will be exerted on, and the force is also going to be directed in the plane of the loop. Now what is going to be the magnitude? Okay, so that is going to be, if you remember, we have seen F is equals to I L B. L over here is going to be the length of the side of that arm. Okay, over here that is B. Okay, yeah, so that is going to be B, and then it is going to exert force F2 on CD. Okay, and F2 is directed out of the plane of the paper. Okay, so that is going to be F2 is equals to IB by B. Oh, sorry, IBB. Okay, again the L over here is going to be B. Now you can see that F2 is equals to F1. Okay, so now if if you have to understand the net force that is there, it is going to be negative. So, oh, sorry, it's going to be 0. Okay, so thus the net force that is there on the loop is going to be 0. And if the net force is 0, there is going to be a torque on the loop due to the pair of the forces F1 and F2. Okay, and the torque itself tries to rotate this loop then. Now over here, this figure is showing a view of the loop from the AD side, okay, from this side. And it shows that the torque on the loop is rotating it is anti-clockwise. Okay, so it is rotating it in this direction, okay, anti-clockwise. Now this torque, if you want to find out the magnitude of this torque, we are going to sum the force, the product of force and the the length and of both the forces F1 and F2. So what you are left with is, since we know F1 and F2 are essentially the same, IVB. Okay, so we write it in this form, and then what you are left with is IABB, where AB is going to be the area of the rectangular loop. Okay, now if we consider a case when the plane of the loop is not along the magnetic field but makes an angle with it. Okay, so suppose over here you can see that there is the plane of the rectangular loop. Yeah, so this is the plane of the rectangular loop. Okay, but sorry, this is going to be your B. Okay, this is your going to be B, but now you have rotated the loop a little. Okay, so this is going to be the loop, so there is going to be an angle associated with this. Okay, so if we take the angle between the field and normal to the coil, and the angle is theta. Okay, so this will be theta. The previous case corresponds to theta is equals to pi by 2. Okay, so over here we were considering theta to be pi by 2. Okay, so that is actually 90 degrees. Okay, so over there the theta was actually kind of perpendicular. Now over here we have 1 theta. Okay, now we can say that the forces on the arms BC and DA are equal and opposite, and they act along the axis of the coil, which is connecting the centers of the mass of BC and DA. Okay, so over the arms, okay, BC and DA. So these are equal and opposite. Okay, the forces on these two arms are going to be equal and opposite, and they are acting along the axis of the coil. Okay, so this is the axis of the coil. Okay, so it is going to be in the axis direction of the axis of the coil. Now since they are collinear, okay, they will cancel each other out, and again there is going to be no net force or torque. The forces on arms AB and CD are again going to be taken as F1 and F2, and they too are equal and opposite. So again the magnitude, because F1 is equals to F2 is equals to IBB. Okay, but now these forces, okay, so F1, you can see F1 and F2 are not collinear. Okay, so again since they are not collinear, they are going to result in a couple, just like we had seen in the previous case where the field and the plane of the loop were in the same plane. Okay, The torque is, however, less than the earlier case when plane of loop was along the magnetic field. Okay, this is why does this happen is the perpendicular distance between the forces of the couple has decreased now. Over here you can see that the the length is going to be a and sorry a and the distance between the two forces, perpendicular distance between the forces over here looks larger than that we see over here. That is why the torque in this situation is going to be less than the torque that we saw in the previous situation. So again we are going to find the torque, the magnitude of the torque with respect to F1 and F2. Now since we have a theta component, we put in sine theta. Okay, so what you are left with is IAB sine theta. Okay, when theta is equals to pi by 2, it becomes 1. So what you are left with is IAB. So that's what we said at the previous, in the previous example, the theta was 90 degrees pi by 2. When theta tends to 0, the perpendicular distance between the forces of the couple also approaches 0. Okay, if your theta becomes 0, then there is not going to be, for the couple. Okay, the forces of the couple will also become 0. Then the forces will become collinear and the net force and torque will become 0, like we had already seen for the arms of BC and AD. Then we can express the torque in a vector product as a vector product of the magnetic moment of the coil and the magnetic field. Okay, and then we can also define a magnetic moment of such a current loop. So that is going to be given as I into A. Okay, so what is A? It is the area vector, the area vector of the rectangular loop, and the direction of the area vector can be given by the right hand thumb rule, and over here it is directed into the plane of the paper. Okay, so it is going inside the plane of the paper. So since the angle between M and B is theta, so you can get the vector. Okay, you over here you can see it's also, we are using sine theta, so you can see that the torque is also vector. So what we are left with is a cross product between the magnetic moment and the field. Okay, and the dimensions of this is going to be a L square, ampere L square, and it is unit is hence ampere meter square. Okay, so this is for the torque on a rectangular current loop. Okay, if your magnetic moment is parallel or anti-parallel to magnetic, suppose your magnetic field is like this. If your M is also in the direction or in the opposite direction of B. Okay, your torque becomes 0. Okay, at in this kind of conditions. So what does this say? It indicates that a state of equilibrium will be reached because there is no torque on the coil. Okay, this will also apply to any object with a magnetic moment M. When M and B are parallel, the equilibrium is a stable one. Okay, so the equilibrium state that is attained when both of these are in the parallel direction. Okay, so that is going to be a stable one. If any small rotation is carried out with the coil, a torque will be produced and which will again bring it back to its original position. When B and M are anti-parallel, okay, the equilibrium is unstable and any of the any rotation that is going to be caused will produce a torque and it will increase the amount of rotation. Okay, in the previous where they both were parallel, they would get it back to the original position, but if they are anti-parallel and if you rotate the loop, then the with respect to the torque, the amount of rotation will also increase. So the presence of this torque is also the reason why a small magnet or any magnetic dipole aligns itself with the external magnetic field. Okay. So now we understand why if we hold a magnetic needle, okay, wherever we hold it, or a compass for that matter, it will always, deflect towards the north-south direction. Okay. So this is the reason. There is always a torque acting on it, and it is usually due to the it is influenced by the external magnetic field of the earth. If we have a loop which has n closely wound turns, okay, like how we saw a solenoid, then the magnetic moment can be given as the product of the number of turns multiplied by the current and the area of the loop. Okay, so this is what we understand from how we can define the torque. Excuse me. How we can define the torque for a current loop. Okay, for a current loop. Over here we are considering a rectangular current loop. Okay, next we will see in the next class what is the torque that will be generated when you have a circular current loop as a magnetic dipole. Okay, over here we were considering only the rectangular loop. Okay, so we will stop here today, and I will continue the next part in the next class. Okay, there are a few more, a few of these torque scenarios, and also we'll try to cover, we'll cover the moving coil galvanometer. Okay, which is a device that is used to measure current. Okay, and it also works on the principle of the correlation or the interrelationship between current and magnetic field. Okay, so thank you. Hope to see you in the next class.